Electrochemistry. This is the last unit in Chem 12. For me, this is my very first screencast. So my goal is to finish this in less than 15 minutes. So that's what I'm going to do. There's a lot to go over, but let's jump right into it. Electrochemistry is essentially the conversion of electrical energy into chemical energy, and vice versa. If you can take chemical reactions, you can use them to produce electricity. And if you have electricity, you can use that to produce chemical reactions. Examples of this are electroplating, where you take electricity and you make chemical reactions happen. And the opposite of that is batteries, where you have chemical reactions and that produces electricity. What is electricity? Essentially what it is the flow of electrons. And if you can follow the flow of electrons in chemical reactions, then you know what electrochemistry is. An example of this is copper and silver nitrate. If you take solid copper and put it into a solution of silver nitrate, you're going to end up with the copper dissolving and with silver being produced on the bottom of the beaker. So over time what happens is our aqueous silver reacts with our copper solid. There's a transfer of electrons and the silver becomes solid and the copper becomes aqueous. So what's happening is electrons are leaving your copper and going to the silver to form solid silver and aqueous copper. You can also see this in an electrolytic cell. And what that is you have two beakers, one beaker full of a solution. In our case, it's going to be a solution of silver. And the other beaker is a solution of copper. And in our case, it's copper. So we have two electrodes that we put into our beakers. And one of the electrodes, in our case, copper, is attached to the other electrode, which is silver. And when you wire them both together and you attach it to a voltmeter, which measures the flow of electrons, you can see that electrons are going to flow from the copper to our silver. In order for this to happen, we also need a salt bridge. And a salt bridge is essentially a glass tube that allows the flow of ions to go through. And when we have a large flow of negative electrons flowing from one side to the other, we're going to need a flow of positive ions from one side to the other to counteract that. If you look at this in terms of two different reactions, what's happening here is we have silver in solution gaining 2 electrons, and we end up with more solid silver. So over time, our silver electrode is going to grow bigger and bigger and bigger as more and more electrons flow towards it. On the other side, the opposite thing is happening. We have copper solid, and electrons are being removed from that copper to make aqueous copper, and it loses 2 electrons. So over time, our copper electrode is going to start to erode. It's going to start to shrink. When you separate out a reaction like this, if you remember previously we talked about one full reaction, the silver, the copper, turning into aqueous copper and solid silver. Here we've split it up into 2 different reactions, and what those are called are half reactions. And in electrochemistry, there's 2 types of half reaction. There's either an oxidation reaction or there's a reduction reaction. And if you think about the word reduction, what does that mean? Reduction means to reduce something or to become more and more negative. And in order for something to become more and more negative in chemistry, you will add electrons. And the opposite effect will happen with an oxidation reaction. The substance will lose electrons. So take a second, pause the screencast, and decide which of these 2 half reactions is an oxidation and which one is a reduction. The silver is being reduced. You have a reduction reaction happening here, and the copper is an oxidation reaction. How do you remember which one is which? For me, I always used rhymes when I was in grade 12, and one method, or acronyms, and what Hebden does is he suggests Leo the lion says grr, and Leo and grr are 2 acronyms. Leo stands for loss of electrons is oxidation, and from that same sort of idea, you can know that GER stands for gain of electrons is reduction. One that I always liked is ox rhymes with loss. Ox, loss, ox, loss. I always thought that sort of rhymed together, and I always would refer to ox as being oxidation and loss referring to the loss of electrons. Or, of course, you can just use simple logic. Reduction, the word means to become more negative. And in order for something to become more negative, you must gain electrons. So whichever one works for you is the best one to use to remember what is reduction, what is oxidation. Two more words that we should add to our list is oxidizing agent and reducing agent. And what these two things are is an oxidizing agent, it essentially causes something to become oxidized. And as a result, it will become reduced. A reducing agent causes something to become reduced. And over time, and as a result, it itself will become oxidized. So again, pause the screencast, take a look back at our example. Which one of our silver or our copper is the oxidizing agent, and which one is the reducing agent? In our example, silver was the oxidizing agent. It became reduced, and copper solid was our reducing agent. It became oxidized. How do we know which one becomes oxidized and which one becomes reduced? A useful tool for this is oxidation numbers. This will come in real handy when we start balancing redox reactions, and that'll happen later on in the unit. What oxidation numbers are essentially fictitious numbers that we apply to elements in order to figure out if it's going to become oxidized or reduced. How do you use them? What you do is you treat each element like it's an ion. So for example, if we have this species, H2P2O4, we will treat each element like it's an ion. So in this example, let's try to figure out what is the oxidation number for phosphorus. So if we treat our hydrogen and oxygen as ions, we know that hydrogen has a +1 charge, oxygen has a -2 charge. So the oxidation numbers are going to be +1 for hydrogen and -2 for the oxygen. Since we have 2 hydrogens, we're going to multiply that by 2, and we have 4 oxygens, we're going to multiply that by 4 to get the total species oxidation number. The key to oxidation numbers is that they must add up to the charge of the whole species. In our example, our species is neutral, so the charge of the whole species is 0. And by simple algebra, if we add up all our oxidation numbers, we find that phosphorus has an oxidation number of +6. But we also know that there are 2 phosphoruses, so one of the phosphorus must be equal to +3. Let's do this for a balanced chemical equation. Find the oxidation number for chlorine before as a reactant and chlorine as a product. So pause the screencast and try to solve this problem. As a reactant, chlorine has an oxidation number of +4. And as a product, chlorine has an oxidation number of +3. Remember that the total charge on the species was -1. As a result, if you compare the two, you start with +4 for chlorine and you end up with +3 as a product. So in order to go from +4 to +3, it must had to have gained an electron. So it was reduced. Let's do this for another example. We have tin and bromine. Find the oxidation numbers for both of these before and after. Which one was reduced and which one was oxidized? Very briefly, tin started out with an oxidation number of +2 and it went to +4. Bromine started with +5, went to +1 or -1. In order for these numbers to happen, in order to go from +2 to +4, we had to lose electrons. In order to go from +5 to -1, we had to gain electrons. So we can say that SN2+ is oxidized and the bromine ion, or the bromine species, is reduced. The last thing I'd like to go over with you is how to read standard reduction potentials of half reactions. This is the last list, or this last graph that you have to have in your data booklet, which you'll now know how to read. It's also on the last page of your Heaven booklet, so if you turn to page 336 and follow along, this will make a little bit more sense. So if you look at this list, you see a large number of reactions. So you see a big list of reactions, and on the left-hand side, you see a large arrow indicating the strength of oxidizing agent. And on the right side, you see strength of reducing agents, going from weak to strong. So looking at those arrows, I can tell you that the top of the list will have strong oxidizing agents, and near the bottom of the list, you're going to have strong reducing agents. So in order for a reaction to happen, you need to have a reducing agent and an oxidizing agent. And this is really similar to an acid-base reaction. In order for an acid-base reaction to happen, you need to have an acid and a base. And this is the same with redox reactions. You need to have a reducing agent and an oxidizing agent. In order for a reaction to happen, you need to have a strong reducing agent and a strong oxidizing agent relative to each other. Where are these on the table? If you were to draw out the table, so if this is our piece of paper in front of us, looking at our arrow, we know that the top left-hand corner has lots of strong oxidizing agents. The bottom right-hand corner is going to have strong reducing agents. So for example, the top one we see is fluorine, the gas, and our bottom strongest reducing agent is solid lithium. In order for a reaction to happen, our hand must move across our table from our strong oxidizing agent. You read the reaction across, and you're going to come down to read the strong reducing agent, and you will read that reaction going backwards. If your hand moves something like this, you start in the top left, you move towards the top right, you go down to the bottom right, back towards the bottom left, a reaction will happen. So an example where this will not occur is if you have both species on the same side of the table, or if the reducing agent is above the oxidizing agent. In both of these cases, there will be no reaction. So for example, what does this mean? If you find both of these species, if you find copper 2+ and Fe 2+, you notice that they're both on the same side of the reaction. In both of these examples, there will be no reaction. So take a second, pause the screencast, find both of these two examples, and see where they land on our table. The other example is when the reducing agent is above the oxidizing agent. So find these two examples as well. So in example 1, there will be no reaction, and in example 2, there will also be no reaction. What is the pattern you see for both of those? So now that we know where reactions won't happen, these are examples where reactions will happen. Find these on your table and see how are they different from the previous examples. You started with silver, and you move, and you also end up with chlorine. When you pair these two together, there will be a reaction. And when you pair copper plus with barium solid, there will be a reaction. So what does that mean, there will be a reaction? An example of our silver and our chromium is the first half reaction you see is silver. This is a reduction reaction. The second half reaction is chromium. This is an oxidation reaction. When you add these two reactions together, you get our full reaction, which is called the redox reaction. So some of the homework that I'd like you to work on are these questions in Hebden. Number 1, 2, 3 to 17. And if you have more questions, we can go over that in class, or you can also talk to some of your peers. Yay, we finished under 15 minutes! I'm very happy this happened. I'm glad you didn't get to see any of the bloopers either.